So I wanted this to be a mostly unscripted video. The last one, as you can tell, took a little bit of working. I'm not a natural marketer. I really enjoy fun turns of phrase, little things like that. But when I started this project, what I started on was a white paper, and it was swarm satellite applications of high energy pulsed solenoids. And as you can already appreciate, that might have taken a little bit of reading for some people, and it didn't get a whole lot of traction. So hence we have the posts from the other day. Now, I've spent the last 2 years working through all the business side to get prepared. Once all the material's out there, I can finally get back to my love of technical detail and analysis. I'm an engineer at heart. I consider the difference between particle acceleration and planetary movement when I was reading Brian Greene's book Elegant Universe. And it wasn't long as a sci-fi nerd until I realized that, wait a second, a lot of these things are elements we already have. So if you're starting with a rough proof of approximation and you want to consider magnitude differences, you can intuitively accept or reject premises. We've got a whole lot more power, the issue's too small, doesn't really matter. So let's go back and look at that assumption for the first set. You've got particle accelerator magnets. They whiz tiny little particles, or fractions thereof, around a 27-kilometer loop at CERN. Now, if you take the radius of a proton, it should be something like 7.66 by 10 to the minus 20 odd. And when you consider this going around a 27K loop at CERN, in the LHC, you've got 2.7 by 10 to the 4. And so you can already see that there's a difference of at least 10 to the 24 in terms of scale. Now, a little tiny particle whizzing along a 27K loop can be accurately held in place by electromagnets. And this is nothing new. You know, we invented niobium titanium wires in, I think the first proof of superconductivity was around the early 60s, and then the Rutherford Appleton Laboratory were building them into cables not long after. So we have the first instance of a Rutherford cable, which is, you know, tiny little filaments of all your superconductors held in a copper matrix, wrap it with some insulators, and that's all well and good, but you do get a lot of cross chatter. So in superconductive electromagnetics, this is little flux jumps in between those superconductive wires through the matrix. And interstrand coupling currents are a serious form of electrical loss and something to be avoided. So the Rutherford labs set out how to build the best cable. And eventually they came to their design, which now bears their name, and it is a series of pairs rolled and twisted around a loop together. And, you know, sometimes there'll be a steel shank in the center, it might be a Xylon strip. There are plenty of options for mechanical support. But the crux of it is, we haven't really come up with any cool new superconductors really since the 60s. We've got NBSN3, which is niobium tin, pretty good for high field applications. And that's seeing a lot more use at present. But at the end of the day, despite all these research grade materials you read about, trying to build a practical magnet out of them that can survive the mechanical Lorentz forces there are only a few options to choose from. So let's go back to our particle along the loop. And, you know, if we're going to push this particle, it's going to take a fair amount of energy. So we can have active magnets the whole way along and it hits the field and slowly slides around. But what's the other, 26.99 kilometers worth of magnets doing? Not a hell of a lot. So if you can pulse the magnets at the right time and incrementally change the velocity, off you go. You only need to activate the magnets in the respective part and your particle beam happily continues along. Now, let's go back to that consideration between particle acceleration and interplanetary travel. If we look at Mars, it's 78.39 million kilometers away. And if you look at a regular kind of satellite, a regular space shuttle, things like that, they vary from, say, I mean, you got tiny satellites, but we're talking about propulsion, so let's talk proper numbers. At least 1 to 10 meters. Make that 1 to the 0 or 1 to 10 to the 1. Even still, 78.39 million kilometers divided by 10 to the 1 leaves you with a much smaller magnitude. So theoretically, we could keep the same size magnets used for particle acceleration, or at least the same force configuration, etc. Let's simplify for now, and achieve an accurate trajectory. Now, if we can control a tiny little fraction of a proton, I am quite sure we can control a shipping container. Now, again, that magnitude difference allows a whole number of other factors to be less accurate, less powerful, etc. If field quality is your measure of accuracy, because you want to know the strength of your magnetic field gives you the push, but that doesn't matter if it's not getting to the destination. So field quality is imperative. Strength, again, tied to the energy requirement. If you think about a 2,000 kilo load and F equals ma, you're shooting for 25g acceleration, 2,000 by 25 by 9.8 should net you just under half a meganewton. If these magnets are in the multi-meganewton size, I think we've got more than enough power to deal with that problem. So not only that, we've got more than enough power, we don't need as big a magnet, and even if we did and could fit a particle accelerator sized tunnel ginormous magnet in space, the configuration's a little off, but the core is still the same. A solenoid is just a coil with a focusing element. In these large scale colliders, what you're looking at is that yoke sits around the outside, and that acts as your focusing to keep the field lines consistent, returning back to field quality. In a simple solenoid, that yoke is just a central rod in the middle. Now, well and good. We definitely can't fit a tunnel-sized magnet up in space right now. But what if you could divide it? What if you could divide it between multiple satellites? And then you start to consider the drone swarming technology. For all the people who were a part of early YouTube, you could watch some drone swarming videos and you would see little quadricopters and they would navigate obstacles, move in and out of buildings, etc. People even started racing them. Now, our first drones were singular, large. They sat towards the upper end of the atmosphere, and the military were using them for years. You can now buy them at JB Hi-Fi for like $200. So if you are able to apply the same technology in a smaller size, in a potentially positive environment, because space is a reasonable chunk colder, heat loss becomes an issue, but also there's no friction from the atmosphere, better for electromagnetic propulsion, and then you consider the application and evolution of drone swarming, you can start to see this looks pretty possible. Now, obviously there's a few more considerations of reality that go into this than this basic example, and this has jumped all over the place. So let's focus it down. When you're training physicists, engineers, or any scientific discipline, you start by making basic assumptions. You teach them to look for basic structures and basic laws, and from there you add all the complexities of reality on top. But if you cannot isolate it in this ideal case, then good luck adding planetary perturbation, all sorts of other craziness that's out there. That's where MATLAB and numerical modeling come in. But for now, let's go right back to high school. The ring launcher experiment is really simple. It's, again, one of these first principle problems where you take that F equals ma example and you look at a simple steel ring and you say, well, it's only a couple of grams. It won't take a whole lot of force to lift off. And you place it on top of a solenoid. And again, simple solenoid. It's just a copper coil, might have a steel or an iron rod in the middle, and it's just mounted on a desk with a standard school power supply. This isn't high-tech gear. This isn't high-power gear. And while there is a forced reaction into the disk and air resistance against the ring and a few other concerns to go in, for now, why don't we just consider Faraday's law, Lenz's law, work out the strength of the solenoid, and then compare A to B. And again, this is highly simplified, but it becomes pretty clear that your little solenoid is able to lift that ring. And you can start to muck around with, do you alter the turn density? Do you alter the density of the ring? Do you make the ring out of a different material? Do you drop the resistivity of the ring itself by cooling the environment? And all these are high school experiments, right? You can go watch them on YouTube. And that proves function. So one of the core problems of space businesses is what's known as the satellite paradox. Now, this is a two-part problem. Essentially, the satellite paradox is that you are unable to prove what you are doing until it's in space. Now, again, reasonably understandable from a cost-benefit perspective. So I do get it. But really, let's break it down. You need to know that A, your components function individually. Pretty fair, don't launch something that doesn't work. Dumb. But then the next step is, will it work in the environment? And this is a key one. So people can argue a very hard line that says it will not function unless it's in space, and you will not be able to thus prove it unless it's in space. Again, reinforcing that satellite paradox. But this isn't the 60s. We have numerical modeling tools that are incredibly advanced. We have so many things in orbit at the moment. We literally have a junkyard problem. And we also have several functional examples that can be demonstrated using high school technology and probably a few more advanced magnets, which we'll come to in a little bit. But as a starting point, not bad. Just like our solenoid example, you should be able to compare A to B. And if you know that your 0.5 meganewton force required is well and truly addressed by your magnet size, then theoretically you are able to divide that between a drone swarm. Yeah, sure, there are reality considerations to put in there. But once you start to solve that force equation of one to the next, it just becomes an n-layer problem. You iterate, and eventually get to the answer that this really does look pretty achievable today. So one of the key idealizations in my mechanics for now is spherical expansion. Now, if you have a solenoid that has a certain aperture, you're expecting to generate a magnetic flux, and this will expand roughly in a cone. And if you look at the endpoints of these vectors for your magnetic flux, you can generalize that as a sphere. I mean, given the concerns of reality, it is elliptical, but again, this adds a layer of mathematical complexity we are not quite ready for yet. Again, we'll return to numerical modeling for that. So this spherical generalization, if you have a grid of 2 by 2, each expanding a sphere from their point of reference, and you have one element with a wing set above, each of those wings is contacted by a focal point of that spherical expansion, giving you the lift of the ring off the launcher. Now, provided there are no major physical laws preventing this function, I don't see why it won't work. The components function, the environment's beneficial, if anything. Solar power and cold, yes please. And, sometimes there might be laws that we just don't know about. I'm a mining engineer by trade. I have taught myself superconductive electromagnetics. I've taught myself everything to do with satellites so far. So I know there is a whole lot that I do not know. But what I can prove has proven pretty conclusive. So if we do consider the satellite paradox. We know the components function. We know the environment's not an issue. And as much as I would love to blast Black Sabbath in space, that is physically impossible. Electromagnetic waves don't have any of the same limitations. So, what do you think?